All right, now that we've looked at parameterization, what we need to do is we need to start doing some calculus with it. So before well, we get too far, some definitions. So parameterized curve, remember this is where we have x as a function f of t, y as a function g of t. So we're mapping out the horizontal and the vertical coordinates for think of it like a particle, where t you can think of as either time or just some parameter variable. It could be an angle, could be anything. Okay, so our parameterized curve x equals f of t, y equals g of t is differentiable. In other words, you can take a derivative of it at t if f and g are differentiable at t. So in other words, you can take the derivative of the parameterization as long as the parameter functions themselves are differentiable. And to do it, it's going to be a bit of a chain rule. So let's say we want to take the derivative of just the y coordinate. To take the derivative of the y coordinate, we take the derivative dy dx. That's the normal derivative when it's not in parameterized form. And we're going to multiply that by dx dt. Of course, this is like a form of chain rule here. So to find the derivative dy dt, it's just the normal derivative dy dx times dx dt. All right, so we'll do some examples of that here in just a second, but we need to rewrite this a little bit because that's kind of ugly. So this leads us to the parametric formula for, so of course, dy dt is useful because dy dt tells you how the vertical aspect of the particle changes with respect to time. Dx dt would tell you how the horizontal aspect changes with respect to time. But almost always we want this derivative, the dy dx. That's going to be the tangent. You can think of it like the slope. That's going to be the change in the particle as it's moving through space, rise over run. So what we're going to do is we're going to take this formula and solve it for dy dx, since that is how we use calculus more often than not. So yeah, basically what we just do is solve that here, and we get dy dx is going to be kind of an awful looking fraction, but that dy dt divided by the dx dt. Oh, that did not turn out the way I wanted it to. Let's try it like this. Dy dt divided by dx dt. A little bit better. Kind of small. Sorry about that. But if you ever need to take the derivative of something that's in parametric form, take the derivative of the y's with respect to t and then divide that by the derivative of the x's. And then another thing is that we don't always just want the first derivative. You can think of that like the speed of the particle. Sometimes we want the second derivative as well. That would be the acceleration or the concavity of the particle. Here we do have to be careful though. So if we're going to take the derivative of the left and the right hand side of this equation up top, derivative of the left hand side, oh, that's supposed to be an x down there, sorry about that. Derivative of the left hand side is just adding on an extra derivative to the function y. But when you take the derivative of the right hand side with respect to x, you just got to be a little bit careful. So we're going to write this as dy dx of y prime, just a different way of writing that. And to do that, I'm just going to kind of give you the end result. What we get is we take the derivative of the derivative, so dy prime dt, and then we're going to divide that by an extra dx dt. All right, and this is a little bit more complicated than it looks. And when we jump into an example here, you'll see. So let's look at an example. Let's say we want to find the tangent to the curve x equals secant of t, y equals tangent of t, and this is going to range through, can I do that? Oh, that's so much faster. All right, so from negative pi over 2 is less than t is less than pi over 2. Okay. Now, we don't want just the generic tangent. We want it at a certain point, so we're going to find this at the point square root 2, 1. Oh, why did it do that? Square root 2 space? Yeah, there we go, comma 1. Okay. So sometimes on the homework questions, they will just give you the point in rectangular form like this. Sometimes they'll just give you the parameter, but know that you can get back and forth. So on this question, they actually give you both. So they say where t is pi over 4. But just know that they may give you the t or they may give you the point, and you can find one or the other very easily. If they just give you t is pi over 4, just plug pi over 4 into the parameterization functions, and this will spit out the root 2, 1. Secant of pi over 4 is square root 2. Tangent of pi over 4 is 1. If they give you the point instead, then set each of your functions equal to that coordinate. So we would set secant t equal to root 2, and the solution to that is pi over 4. And we would set tangent of t equal to 1. The solution to that is pi over 4. Okay, so if we're trying to find the tangent to the curve, to find the tangent to the curve, what that's really asking us to do is to find the equation of the line that has the same slope at that location, at that point. So if we want to find the equation of that line, first we need to find the slope. All right, and to find the slope, that means that we're taking the derivative, right? The slope, that's that dy dx at that certain point. So let's go ahead and just find the generic form of the derivative, and then we'll plug the point, or maybe we'll be plugging the t's, we'll see here in a second, into it. So just copying down the formula, remember dy dx from up above here is dy dt divided by dx dt. So for us, that's going to be the derivative of y with respect to t, the derivative of tangent is secant squared. And then we're going to divide that by the derivative dx dt, which is the derivative of secant. The derivative of secant is secant times tangent. All right, and then this will simplify down a little bit, right? So one of the secants will cancel out on top and bottom. We'll get secant divided by tangent. And that may simplify down a little bit as well, but it really doesn't matter because we're not looking for this form. We want to know what this answer is at the location. So notice that we have t's in here. We're not going to be plugging in the point. We're going to be plugging in the parameter t equals pi over 4. So plug in t equals pi over 4. And when we do that, we're going to get secant of pi over 4 divided by tangent of pi over 4. Secant of pi over 4, that's the square root of 2. And that's going to be divided by tangent of pi over 4, which is just 1. So we get that square root of 2. So that is going to be the slope at this location for this curve. Okay. Last thing is, of course, we're trying to find the equation of the line, right? We're not just going to be using the slope, but now that we have the slope, we can use the point slope form of a line. And I'm sure it's been a little while since you guys have looked at point slope form stuff, but this is the equation y minus y1 is equal to the slope m times x minus x1. I hope that looks somewhat familiar from algebra. So just plugging in what we know, we're going to do y minus the y1 of the point, which is 1, and that's going to be equal to the slope, square root 2, times x minus the x of the point, square root 2. All right, and then we would just simplify this down a little bit. So we would distribute that square root 2 into the parentheses there. When you multiply square root 2 times square root 2, you're just going to get 2. The square roots cancel out. Trying to get y by itself now, so we would add that 1 over and get this. So y equals, oops, that's not supposed to be a square root of x. That's supposed to be a square root of 2 multiplied by x. Sorry about that. So distributing the square root of 2 into here, we get square root 2x minus 2. Same thing down here. That should be square root 2 times x. There we go. So this is going to be the equation of the line that is tangent to the curve. I'm going to pause it real quick and see if I can get a picture to show you what's going on. Okay, so starting back up the recording, I brought up Desmos here. Desmos lets you graph things in parametric form. So if you type it like this, parentheses, and then the first function, comma, the second function, close parentheses, this is saying x equals secant t, y equals tangent t. It also goes ahead and pops this in here. So remember we were graphing from negative pi over 4, was it? Nope, these are supposed to be negative pi over 2. Sorry, I should have looked a little bit closer. So we were graphing from negative pi over 2 to positive pi over 2. So this is what our parametric curve looks like here. Okay. But we wanted to find the tangent to that curve at the point root 2, 1. So the point root, oh, can I graph just a point? Let's see if that works. So if I do square root 2, comma 1, Oh, it does graph a point. That's so cute. So there's the point square root 2, 1 on our function. And remember, we wanted a tangent to that. So a tangent to that is going to be a line that just touches that location with the same slope as the red line here. I've already written the equation here, so I'm just going to go ahead and graph it. And there you go. So you can see that the solution that we got, y equals square root 2x minus 1, really is a tangent to the parametric curve at that location.